2022. Thanks, Anthony. We are really excited for a new year of seminars, and we're especially excited for Tim to kick us off for his really exciting talk. Just a few quick announcements. If you haven't already, please sign up to our GeoDAWG mailing list. We have now kind of over 100 subscribers, so it's a really good community that's forming, and we're really excited about that. So please make sure to join that if you haven't already. As you can see down on the bottom, we have our upcoming seminar schedule. Our next seminar is actually next week, so please make sure to join us next Tuesday to hear from Dong Lai on his work on radiation belt dynamics. And Tim is nice enough to let us record this talk as Anthony has done, and we will make that recording available on our YouTube channel, and you can find that link on our seminar website page, and Tim's right where you see the title of his talk will be a link to that video, so you can come back and check out the talk again there. And again, we're filling out our schedule throughout the year, so please check back as we will be updating it and more speakers in the future. And again, if you have any suggestions or any ideas or topics you want to discuss, please feel free to contact us as well. So now I'll turn it over to Anthony, who will introduce our speaker for today.
Hello, everyone. Welcome back. Just a few quick rules of the road is please remain muted unless you're actively speaking, out of consideration for the speaker. And also today we're actually going to try and save most of the big questions for the end. So when it comes time, either put your question in chat or raise your hand. We can get to it. If conversation is completely dead, just go for it, of course, but just to try and keep everything a bit organized. And so our speaker today is Tim Kodikara. He's currently at the German Aerospace Center's Institute of Solar Terrestrial Physics. He got his PhD from RMIT University in 2019, and his research interests are numerical modeling of the magnetosphere-ionosphere-thermosphere system, thermospheric variability and electrodynamics, and of course data assimilation, which is why he is here to present to us today. He'll be telling us about data assimilation in TIE-GCM. So thanks very much, Tim, for speaking for us today, and the floor is yours.
Awesome. All right, let me.
Thank you for that introduction. Let me try and share my screen. Is that all good?
Mm-hmm.
Yes, looks great.
Awesome. So yeah, thank you for that introduction. First, I want to thank you, Adam, and Anthony, and the organizers for giving me this opportunity to talk to you all. So I work at the Institute for Solar Terrestrial Physics at the German Aerospace Center in this beautiful city of Neustrelitz. Before the pandemic hit, I used to commute to this beautiful site. Yeah, so we are a relatively new institute. If you find some common interesting topics, please feel free to get in touch with us. So today I'll be talking about data assimilation in TIE-GCM. I will first briefly introduce data assimilation, basically in the context of ensemble data assimilation, at least just enough material to make sure that we're all on the same page with some of the jargon. And then I will explain to you how we drive TIE-GCM model, and then quickly jump into some results with data assimilation using cosmic radio occultation derived electron density and some other data along the CHAMP satellite. So data assimilation is this, I'm gonna try and minimize this video screen. It's on top of my slides. I don't know if I can do it right there. Data assimilation is the simple sounding idea of combining observations with a forecast of the system to produce an improved estimate of the state and its uncertainty. And in the talk, today, and now it's not moving forward. Okay, there you go. In this talk today, in my results, we mostly use ensemble data assimilation, so we'll focus on that. And obviously, although it sounds simple, it gets hairy a lot fast as we move into the complex. As we move into using complex models. But anyway, this for ensemble data assimilation, the base theorem, the base rule is the key. What this theorem basically tells you is that you can have an updated state. You can have an estimate of your model state at time t sub k, current time, let's say, given all the information you have of the system specified here using the uppercase y at time t sub k. So this uppercase y includes all the observations plus your model knowledge. And you can have this analysis or updated state using the probabilities of observations at current time step given its model state, and combining that with a forecast of the state at time t sub k using all the information you have prior to that. To visualize this idea, so one could start with some model forecast of the state. So these are each asterisk here is a forecast of the state of the same state, representing different ensemble members. One could use the statistics to generate a probability distribution function, basically the mean and the standard deviation. You use that information, and also one could get the observation likelihood from your observing system, so the observation and the observation error distribution, and combining that gives you your updated state, the analysis state. And it turns out you don't have to worry too much about the denominator here, because the denominator is just the area under the product of the numerator. So basically, when we say we have an improved state or an updated state, what we mean is this distribution represented by this blue line, or in other words, this shifting of the mean and squishing the variance is how we improve the state. So by design, the analysis is more confident than either of the other two PDFs. When we want to advance the ensemble, we map each ensemble sample to the observation space using a forward function h. This could be something simple as interpolation or a whole different model. And then you combine that information with the observation error distribution, use that information to compute the increments for the prior observation ensemble, and then translate that information back to or linearly regress that information back to your desired state variables, and use that updated state to move forward. And this is what we would call a forecast. Right. So here I will stop and advertise DART. DART provides state-of-the-art ensemble assimilation tools. It has excellent documentation, lots of great tutorials, and to start learning from toy models to huge models. And I use DART assimilation tools to assimilate data into this model of the upper atmosphere called thermosphere-ionosphere-electrodynamics general circulation model, TIE-GCM. In short, it's a physics-based self-consistent model that extends from roughly about 100 to 600 kilometers in altitude, depending on solar activity. I will briefly describe the boundary conditions we used in this model. We use a low resolution model, low resolution version of the model, 5 degree by 5 degree in lat and lon, and to specify the high latitude energy input, we use the Healy's ion convection model, which is driven by the Kp geomagnetic index. And to specify the solar radiation, we use the F10.7 based EWARC model. And then we specify the auroral precipitation using the Rubble and Ridley parameterization as which is a default option in the model. And then the low atmospheric forcing is specified using the numerical model global scale wave model, as well as the Dayofear dependent eddy diffusion coefficient. So once you specify these boundary conditions and hit go, TI-GCM can basically give you everything you need to describe or represent the thermosphere-ionosphere system, so plasma quantities and neutral quantities and so on. Okay, so we have a model and we have an assimilation system. Now we need to generate the first prior ensemble to start assimilating things into. Here I follow a very simple, perhaps too simple method. What we do here is we perturb some of the key forcing parameters in TI-GCM, namely the solar input and the high latitude energy input. Using these parameters, daily F10.7 and the 81-day centered average F10.7, as well as the Kp index. We generate a normal distribution of these parameters and use a non-repeating combination of these three to drive each of our ensemble member and keep that constant. Right, now a couple of words about the state vector. To illustrate this, I used this nice paper by Cheating Su, published in 2014. They conducted an observing system simulation experiment using TI-GCM DOT, where they assimilated synthetic electron density. So basically, the idea I'm driving at here is if you assimilate electron density and update only electron density, you get this blue line here. They show the root mean square error of electron density after an assimilation. These dots are the forecast states, and these NT squares are the analysis states. So if you assimilate electron density and only update electron density itself, you see that during the analysis step, the root mean square error reduces, but in the forecast step, it goes back up to the background or the control level. As you include different the plasma and neutral quantities, this behavior changes. So in this study, they concluded that including both plasma and neutral quantities in your state vector improves the accuracy of both the analysis and forecast while doing the assimilation. They also used this study to show that they also use this study to show that it's more important to include O plus in your state vector to get an improvement in your forecast much more than much more than including temperature or neutral winds, basically referring to this green line down here, where they include both O plus and the other neutral parameters. You get a slightly better persistent forecast for a limited period of time. Okay, so in our studies also we follow, we use a similar state vector similar to this number 6 green line, with some minor differences. When it comes to that, I will specify those. Right. Okay, so in the next few slides, I wanna talk a little bit about this our recent paper where we investigated the impact of solar activity on forecasting the upper atmosphere via assimilation electron density data. Here what we do is we assimilate radio occultation derived electron density data from cosmic into TIE-GCM. These these RO profiles are globally abundant, so it's a great source of data to test the effect of assimilation on the model forecasted state on a global scale. That was one of the motivations for us to do this. So we did 2 experiments, one representing solar minimum conditions, which we label as E1 in March 2008. So here I show the F10.7, fairly low on top here, and the geomagnetic activity shown via KP index, AP, and DST also shows that it's relatively low, nothing much going on there. And we assimilate data for 4 consecutive days, starting from 4th of March until 8th of March. And in our second experiment representing solar maximum conditions, F10.7 slightly moderately high, and KP geomagnetic activity is also low, like we wanted. Here too, we assimilate data for 4 consecutive days. Now, looking at the results, here I'm presenting model data bias in the assimilation results as a function of latitude and altitude, and the color bar gives you the model minus cosmic electron density data. So on top here is TIE-GCM minus cosmic, and then analysis, forecast like we explained before, like I explained before. And then I have also included another run called eval Ne, which stands for evaluation no assimilation. It's also a fairly simple idea where we run the ensemble with no assimilation whatsoever. This gives us a direct measure of the impact of assimilation on the analysis and forecast state. Right, so the first thing from this figure I want to highlight is that assimilation has significantly reduced the model bias in the analysis state. There's also one thing to highlight here, perhaps systematic to TIE-GCM in these high latitudes, in these southern high latitudes, the model bias is fairly low in all 4 comparisons. But even their analysis is slightly lower. And then also there are these black lines representing the height of the maximum electron density of cosmic in solid black line, and which corresponds to the model is shown with a dotted line. Dotted line. The reason where we have an incomplete vertical column, let's say, we don't give the height information for incomplete columns. The reason I overplot this maximum height information is to show that interestingly, in some areas, the data assimilation has corrected the maximum height in the analysis state, but not so much visible in other parts of the analysis state, or even in the forecast state here. Now we can compare a similar figure for the E2 run representing solar maximum conditions. Here too, I will straight away highlight that the analysis is much more improved or less biased than the eval Ne run, for example, but not much difference in the forecast state. Here too, we can see that although the analysis bias is low, in the northern high latitudes, data assimilation has changed the maximum height, let's say, in an undesirable way. So it doesn't correspond very well to the cosmic height. But in other areas, it has still corrected it. But nothing much is seen in the forecast state. So comparing these two figures, we conclude that the agreement between forecast electron density state and data, cosmic data, is better during solar minimum than solar maximum. When we did this experiment, or the way we designed this experiment, we also noticed that a lot of observations are discarded during assimilation. So I want to show you some of those statistics, along with an opportunity to glance at some other important statistics, such as the Pearson correlation coefficient and the sigma difference, which is sigma. The standard deviation of the model minus standard deviation of cosmic data. We use this statistic absolute difference of the standard deviation to see how close or ensemble or our analysis or forecast, how close the variability in our analysis to that of data, for example, and then root mean square error. And these statistics are given for TIE-GCM analysis and forecast in these three columns. And here I show the percentage of the assimilated data from all the available cosmic data. We have one column for E1 and another column for E2 solar maximum for different altitude levels. So you see in these low altitude regions, only a small amount of data are assimilated into TIE-GCM. This is by design, where we discard observations that are not within 3 sigmas of a prior estimate. And then in higher, and then we can continue these statistics to higher altitude levels, where we notice that obviously the assimilated percentage improves a little bit, but always below 50%. So a lot of data are discarded here. And then looking at the sigma difference, it's significantly low in these high altitude regions, above 300, compared to the standalone TIE-GCM run, but not so much visible in these low altitude regions. We also can obviously see that the root mean square of the analysis state is low compared to the other two. Right. This figure illustrates that the assimilation of cosmic electron density also impacts the neutral mass density state here. On the left-hand side column, we have neutral mass density as a function of a Latlon map of neutral mass density for TI-GCM for forecast and analysis. And on the right-hand column, we have the bias, forecast minus TI-GCM as a percentage, analysis minus TI-GCM, and forecast minus analysis. And these blue dots correspond to the cosmic data, or represent the location of cosmic data that were assimilated in this assimilation window corresponding to this snapshot. The summary of this figure is that there's some difference seen in these two, forecast minus TI-GCM and analysis minus TIE-GCM. A lot of this difference is due to the forcing difference between the standalone TI-GCM and our ensemble. But one could also notice that where the data were assimilated, there are some notable changes to the neutral mass density state. So, for example, right here in this northern latitudes above 45 degrees here, it suggests, or this difference suggests that assimilation of electron density suggests that the neutral mass density should be about 10% higher than what the standalone TI-GCM run estimates. With that, I move on to show some results from a recent study that we did using data assimilation to improve neutral mass density estimates along CHAMP. Here, the idea is also fairly simple, but sort of a motivation for this study. So the CHAMP satellite carried an accelerometer. One could use the accelerometer measurements to derive in situ neutral mass density through its relationship to atmospheric drag. But this process is not straightforward, and there are several methods to do it. For example, I'm showing 3 such different data sets here. For example, in orange, we have Eric Sutton's data set. In green, we have TIE-GCM's data set. And in gold, we have Piyush Mehta's data set. There are obviously some differences between the 3 data sets. So depending on what paper you look at, if one of these data sets is considered as the truth. On top of that, the uncertainty of accelerometer-derived neutral mass densities are also not fully understood. So here, what we wanted to do was assimilate some other in situ measurements from the CHAMP satellite into TI-GCM. So we chose electron density and electron temperature measurements from CHAMP. We conducted 2 experiments. The first one, which we label as E1 10%, where we assimilate CHAMP electron density and electron temperature with 10% uncertainty. In a second experiment, we assimilate the same set of data with 100% uncertainty. We also conducted a third experiment where we retrieve neutral winds from the horizontal wind model along the CHAMP orbit and assimilate that back into TI-GCM with 10% uncertainty. The one motivation to do this third experiment is because horizontal wind model 2007 was partly used to derive the CHAMP TU dataset that I showed you earlier. Okay, so here we compare our assimilation results with ground-based observations. Here I'm showing a plot where I compare electron density from ISR stations in the northern hemisphere high latitude. So we have We have Pucker Flat, Tromsø UHF, Tromsø VHF, and Sonderstrom. And we have our data assimilation experiments, E1 and E2, where we assimilate champ electron density and electron temperature, and our H7 10%, where we assimilated neutral winds. And we compare these with co-located observations from these beg your pardon, ISR stations. Sorry about that. We define co-located observations as within 5 kilometers in altitude and within 2.5 degrees in latitude and longitude. So the champ electron density that I show here with a magenta C are the same data that were assimilated into E1 and E2. I see more often than not, these blue lines and the orange stars coincide with champ electron densities. But one key thing to highlight here is that both H7 and E1 and E2 runs can see that the data assimilation of any of these data has pulled the model from the eval Ne state toward ISR data in this limited amount of data that we have to compare. That's the main point to highlight there. And here a similar comparison, but now for electron temperature from ISR stations. So similarly, we see E1 and E2 show some good agreement with champ and ISR data, but not no notable improvement on this green plus sign, which is the H7 run where we assimilated neutral winds. But some impact is visible in some comparison, but it could also be purely coincidental. Right, now the objective was to look at the impact on neutral mass density. So I'll be showing a few plots like this. So to introduce this plot, these black lines with different markers gives you the champ neutral mass density from champ, these different champ density data sets. These are orbit average neutral mass density for the assimilation period, 4th to 8th of March, and the gray line here is the TIE-GCM standalone run. We also bring in some commonly used empirical models to compare. Immediately we can see that the recently released HWMo7 database and also the Czechia Bowman 2008 model shows some good agreement with the champ ES dataset here. Also, one other thing to highlight here is that the empirical models are doing a far better job capturing the day-to-day variability in neutral mass density compared to the standalone TIE-GCM run. So now if we look at our assimilation results, in the experiment where we assimilated neutral winds, this H7 10% run shows a great agreement with champ data, a qualitative agreement. For reference, I've also included an evaluation no assimilation run here. In the two experiments where we assimilated plasma quantities, we see much more significant variability on the neutral mass density state. But in all three experiments, we see that the data assimilation has pulled the model toward champ data somewhat. Right, so this significant variability seen in E1 and E2 could also be due to the assimilation window. We use a relatively short assimilation window of 10 minutes. Because electron density variability is much more larger than that of neutrals. So when we keep assimilating every 10 minutes, perhaps the variability to introduce to the model is too much, or even maybe chaotic. That was orbit average neutral mass densities. Now we can also look at the impact along the orbit. Here I'm showing the bias in neutral mass density. So model minus champ data for TIE-GCM, eval Ne, and R3 data assimilation runs. And at the bottom here, the champ neutral mass density. First thing to highlight here is all along the orbit, the H7 run shows a low bias. E2 run is slightly better than E1, but this kind of visualization also helps us to identify regions where there's a higher bias or lower bias. So, for example, even though H7 performs better, we also notice that nighttime in nighttime northern high latitudes, the H7's bias is slightly larger. Interestingly, in the southern high latitudes, all three data assimilation experiments have slightly lower bias. So I will conclude now with some model performance statistics from this experiment. So to show the model performance, we use mean percentage deviation as a statistic. Mean percentage of the model estimate relative to observations. So using this expression, these dotted bars gives you the mean percentage deviation using champ TU as observations in this expression, and this plain bars gives you the mean percentage deviation using Eric Sutton's champ dataset as observation in this expression, and then we compare with several different models. But this figure is for a slightly larger period, 2-month period, February to March. And now these statistics are for the assimilation period, 4th to 7th of March. The reason I'm showing this is to highlight that the statistics that we have for the assimilation period for the models are also similar to what we get with a larger data set, so somewhat representative of this large data set. So to add an extra layer of confidence to the statistics that we see during the assimilation period. So in general, all these negative numbers shows that the models overestimate, but we also saw that the Eric Sutton's dataset is slightly has slightly larger neutral mass densities compared to champ TU. So the models agree with champ E is better than with champ TU. Our H7 run has the best agreement with champ TU in all of this comparison. Yeah, I think that brings me back to the first slide. So that's all. There's also lots of other studies using TIE-GCM and DART. If you go to the DART website, I guess shouldn't be too difficult to find some of these publications that describe some of the other excellent research that they've done using TIE-GCM and DART. So I'll stop here and take some questions if you have. I guess there's still time for questions.
Yeah, absolutely. All right, thanks very much, Tim. That was a very interesting presentation. Do we have any questions from the audience? All right, just to get us started, I had a question on one of your earlier slides, actually showing some results from Su et al. 2014. Oh, we also have a question to follow up with afterwards. This will just be a quick question. They were looking at how the RMSE improved based on which states you assimilated. Was it kind of intuitive based on, did it make intuitive sense that when you added certain quantities that improved, the model improved in certain ways, or was that is the connection between those two unclear? And I guess more generally, does that approach of just adding assimilation of specific variables help you reveal new physics at all, do you think?
Yeah, I think it was fairly intuitive because you want to.
Might be a strange question. I have no idea about ion neutral interaction models.
Yeah, so for example, you don't want to include some quantities in your state vector that have no physical relationship. So if you're assimilating electron densities and wants to update, let's say, quantity X, which has no physical relationship to quantity X, then it doesn't make sense to include that in the state vector, and it's also dangerous because can introduce something what they call spurious correlations. These are all statistical updates to these unobserved quantities. So it's important to include whatever quantity you want to include in the state vector with some good reason. Yeah.
Sure. Yeah, that makes sense. Okay, Victoria also has a question. Feel free to unmute and ask yourself if you want, otherwise I can read it out for you.
Hi, Tim. Yes, thank you for the talk. Very interesting. I have a question. What approach did you use to form your covariance matrix? Did you use any localization, if yes or not? And what about localization in vertical direction?
Right, that's an excellent question. What approach did you use for the model error covariance formation? I'm reading your question again. Model error covariance formation and localization in horizontal. Okay, excellent. So for localization, we use the Gasperi-Kohn function on the horizontal, and in the vertical about 40 kilometers, so not too much, at least with when we assimilated data along champ orbit. But with cosmic, I think we used we didn't discriminate on the vertical much, and we used the ensemble adjustment Kalman filter to update the states. It's an ensemble square root filter.
Thank you.
Does that cover?
Do we have any other questions?
I had a quick question. In some of your earlier slides, when you were looking at the effects during solar minimum and solar maximum, comparing your simulation to cosmic, I believe there was some difference in the altitude peak at higher latitudes. Could you just explain a little bit why that is the case that you're finding?
Some difference as in like in these low altitudes?
The higher latitudes.
higher latitude, some difference in the.
Yeah, I think it was mostly during solar maximum where it was.
Okay, sorry.
Yeah, the bottom left-hand plot on the right-hand side.
So why the maximum height jumps? That's a good question. I actually honestly don't have a straightforward answer, but it could also be due to in high latitude electron precipitation. If but and then yeah, we didn't have a huge geomagnetic activity that could explain big jumps. But yeah, in the high latitudes, I would assume you can get electron density enhancements.
Great, thank you.
Nick, go ahead and ask your question if you want.
Yeah, hi, Tim. Nice presentation. I had a question. Could you say a bit more about the results showing the assimilating the neutral winds from an empirical model having more impact than the actual data along the track? Is that, I maybe don't quite get the interpretation there. Is that essentially saying that if you had good neutral wind measurements, that would be even better than having in situ electron density data? Or is it something about the, say, correlation behavior between the different quantities that you're assimilating?
Yeah, I think one of the primary reasons why we see good correspondence with this H7 experiment is probably because when we introduce some changes to the neutrals, it persists in the model, and these differences are also not so. So these updates are also not so large and disruptive to the ensemble state as what I would get from updating electron density, because that correspondence with the ensemble that correspondence with the ensemble electron density with champ electron density is quite large. The other reason I can think of is these H7 winds are the same winds that the champ TU uses. So basically, we assimilate the same winds that they use, which helps the model to adjust the neutrals in the same direction. I think those are the two things I can think of. With electron density, it's much more noisy. So for with a 10-minute window, I think we are introducing a lot of changes to the model, and then in the next 10 minutes, the electron density is something else, and it introduces, I guess, what I'm trying to say is it introduces too much changes that the next 10 minutes is not enough for the model to, I guess, recover. But I haven't done an experiment with a long assimilation window to conclude that statement, so can't really say it conclusively. But yeah, that's one of my guesses.
All right. Any final questions for Tim today? Okay, so hearing none, thank you again very much, Tim, for coming and talk to us today. It was a very interesting talk. And yeah, Adam, if you want to just announce the next talk we're going to have one more time.
Yeah, just want to reiterate that. Thank you, Tim, again for a really great talk, and thank you all for coming and attending this this GeoDAWG seminar. The next seminar is actually a week from today, so please come back next Tuesday, February 1st at 11, where Dong Lai Ma will be giving a talk on their radiation belt modeling work, and then we'll have more talk coming up. I think we'll have a solar talk in March 1st, and then some more coming in at the end of April. And again, look out for, we'll be making this a recording available on our YouTube channel, which we'll link through our website as well. So thank you all again. Thank you, Tim, especially for a great talk, and thanks everyone for coming, and we'll see you all next Tuesday.
Wonderful. Thank you. Thank you all.
Bye, everyone.
Thank you. Bye.